Hello there. In this lesson, we're going to learn about reaction mechanisms, an example of which is how ozone is destroyed by chlorofluorocarbons up in our upper atmosphere. So when those CFCs, which are used for a bunch of purposes, or used to be used for a bunch of purposes down here on Earth, whenever they get out into the environment, they're kind of persistent. They don't break down very easily. And eventually, over time, they find their way up into the upper atmosphere where they cause a lot of damage. So what happens is that ultraviolet B radiation will hit these CFCs and cause one or more of these chlorine atoms to break off. So that's called a chlorine radical. And you see that single electron that's on the side there. That means it's really reactive with other compounds that it bumps into. So when it bumps into an ozone molecule, which is like O3, what it'll do is it'll break off one of those oxygens, breaks one of these guys off, and you end up with some oxygen gas that's formed, and then that single oxygen's bonded to the chlorine. When one of those bumps into another free oxygen that is floating around up there, as sometimes happens, that'll break this chlorine free. You'll get more oxygen being produced, and you'll have that radical back. So the radical sort of acts as a catalyst because it can cause the breakdown of hundreds or thousands of ozone molecules before it might react with something else that renders it inert. So that process is a mechanism when there's a bunch of steps or bonds are broken until you get to some final products. And you see that there's some in-betweens that also exist only sort of temporarily that we call intermediates. Okay, so let's learn a little more about that. So a mechanism is basically a series of steps, chemical steps, that you can add together kind of like you did Hess's law, right? You can add up the steps of a mechanism to get the overall reaction. So these steps, or elementary steps as they're sometimes called, they're always going to include some intermediates. Either an intermediate will be made or an intermediate will be used. Intermediates are particles or molecules that are there temporarily while the reaction is going, but when the reaction is done, they're not present. So with the ozone thing, that OCl molecule, that's an intermediate because it was made, it was made in one step and then consumed in the next step, and then the overall reaction here is O3 plus O makes two O2s. You see this here was a catalyst because it was there at the beginning and then it was produced later on as a product at the end, so it never really got combined permanently with another particle. So just to review, intermediates are formed and then consumed before the reaction is done. And catalysts, I'll use a different color here, catalysts are present at the beginning and then get regenerated at the end, right? So catalysts are the ones that are there at the beginning and then get regenerated at the end so they can continue to catalyze other reactions. And the intermediates are the ones that are generated early in the mechanism and then get used up before the reaction is done. So comparing reaction mechanisms to Hess's law sometimes has a few flaws. And so I want to point out the main difference between a mechanism and just random equations that can add up together. So with a mechanism, there's always going to be intermediates, right? There has to be a link between one step in the mechanism and another step in the mechanism. And so that's what we have here in the first reaction here, where we have C as an intermediate, and then it gets used up in the second step. In the second example here, there is no intermediate, and therefore it's not a mechanism. It's just two random reactions that happen to add up to an overall reaction. The other thing that has to be present for a mechanism to be valid is that it has to add up to the overall reaction that you are observing. So this one also has a catalyst. We'll get rid of that. We'll get rid of the intermediates, and we end up with 2 B's make E plus D, right? Here there are no intermediates and there is no catalyst, but you have the same overall reaction. So one of them is just Hess's law, 2 random reactions that add up to each other. The other is a mechanism with intermediates that connect them. So ding. Another neat thing about a reaction mechanism is that the coefficients in the elementary steps will match the exponents in the rate law for that step. So if we're looking at step 1 here, the rate law would be R equals some constant, and then it'd be the only reactant is NO2Cl, and since that's an invisible one there, it'd be an invisible one here, right? And then for the second one, second step will be the rate law for this one, will be the constant equals the NO2Cl, but also the chlorine on its own, the chlorine radical. So since both of those are ones, of course there's ones as well, you don't have to write the ones. So there you go, the coefficients match the exponents in the rate law for each step. Now in a reaction mechanism, you can think of each step as having its own speed or rate, and therefore if they're not all the same, which obviously they probably wouldn't be because these are all different reactions going on here, different bonds being broken and all those other factors, the reaction can only go as fast as the slowest step. So if you have an example here and you're pouring some water, let's use some blue for some water. So we pour some water in here, and then it runs out, nice stream. And then for this one, it runs out at sort of more of a trickle because it's a smaller funnel. So this funnel here would determine how quickly the water could come out the end. I'm assuming it doesn't run over the side. So this would be rate determining, be the second step. In this case, we've got the smaller funnel on step 1. And so this one here takes in the original reactants, and then you're going to get intermediates come out at whatever the rate is for that smaller funnel. And it doesn't matter how big this one is, it can still only come out at the same rate as it can gather intermediates from step 1. So in this case, the rate determining step would be step 1. So in this example, we have step 1 as being the slow step and step 2 being faster. So that means the reaction can really only go as fast as step 1 goes. Step 2 is just going to have to wait for intermediate to show up in order for the reaction to continue. So that means that the overall rate law, the expression, will be the same as the rate law for that first step, for the slowest step of the reaction mechanism. And that also means that it's a way, because rate laws come from experiment, that you can use your experimental data to verify whether or not your rate law is valid. All right, so what happens now if the rate is governed by the second step? We flipped and we made the second step the slow step. So now the rate law for this whole reaction is going to be the same as that second step. So it's going to equal the constant times NO2Cl times Cl, and that would be your rate law. However, this is an intermediate. That's not a reactant, that's an intermediate. So we have to include the concentration of the substance that will produce that intermediate. So the intermediate came from the previous step, which means it's this reactant, which happens to be the same reactant as in the second one, is what determines the concentration of those chlorine radicals. So we're going to sub in the rate for this guy. So this was determined by the constant times the concentration of NO2Cl. So really all we need to do is put that part in here. This constant is going to blend in with the other constant. And what you'll end up with then is the constant times NO2Cl. And then we're going to sub in NO2Cl for this guy. And then, of course, you can combine them. So the constant equals NO2Cl squared. And that'll be your overall rate for this overall reaction. Hi, so energy profiles are another way to show the steps of the mechanism and indicate which one is slower or faster. I'm going to do an exothermic reaction. So for reaction number 1 here, if you start with your reactants here, and then you have 2 steps where the first step is the slowest one. So to show that it's slowest, we're going to give it the greatest amount of activation energy. And then for the second step, it'd be a lesser amount, and then finally you'll end up with your products. Conversely, if the second step is the slow one, well then you would give the first step sort of a smaller activation energy, and then a bigger amount for the second step, and then finally to your products. So there you go. Since this quantity here is less than this quantity here, that would tell you that step number 2 is the slow step. Okay, finally, just to summarize, the things to look for to see whether your reaction mechanism is plausible or possible is to make sure that they add up to an overall reaction. So let's see what we have here. Looks like we have intermediate here. We've got 2 A's plus a B making D. So if that's the overall reaction you have, then great. You have to have intermediates that connect the steps together. So there we have our intermediate. And we have to have the slowest step have coefficients that match the rate law. So if this is our slowest step, we have A and C. A and C are reactants in the second step, but C is an intermediate, which means you have to back up to where C was made here and also include A and B as well. So that's 2 A's and a B, 2 A's and 1 B. And that means ding, ding, ding. All 3 are satisfied by this mechanism, so that means it's a good mechanism. Okay, hope that helped. We'll talk to you soon.